If you're old, like me, maybe you remember this game. It's called Blockout, and it's essentially a three-dimensional version of the classic Tetris. It's pretty neat. The way it was originally played is you moved the block with the arrow keys on your keyboard, and you rotated the block using the Q, W, E and ASD keys, and you dropped the block using the spacebar. Which works, but it's not the most intuitive way. Since then, we have invented special controllers that can be used to manipulate objects in 3D space. They came in many shapes over the years. This is the modern iteration. It's the 3D Connection SpaceMouse Compact. They are mostly used with 3D modeling and CAD software. For example, here I'm using it to rotate an object in Autodesk Fusion. What's cool about it is that you get all the degrees of freedom at the same time. You can rotate the object around whatever axis you want, while simultaneously translating it in space. Let's try and use it to play Blockout. We are going to use HID Remapper to map the 3D inputs from the SpaceMouse, the rotations and translations, to keyboard inputs. HID Remapper is a universal adapter for USB input devices. Instead of plugging an input device directly into your computer, you plug it into HID Remapper, and then you can configure it to map some inputs to other inputs. First, let's do a quick demo, and then I'm going to show the HID Remapper configuration that I created to make it possible. I'm going to disconnect the SpaceMouse from my computer and plug it into the HID Remapper that's also connected to my computer. First, let's open Notepad and see that the SpaceMouse is actually generating keyboard inputs. Okay, let's play Blockout. I am now playing Blockout with the SpaceMouse, which in my opinion is a lot more intuitive than playing it with a keyboard. Let's try to clear a line. Or I guess in this case it's not a line, it's more like a layer. Okay, enough of that. Let's see the configuration. As you can see, we have 4 mappings for the arrows, 6 mappings for the Q, W, E, ASD keys that do the rotations, and spacebar for dropping the block. All of these mappings have registers as their inputs, which means there's also an expression that's putting values in these registers based on what inputs it reads from the SpaceMouse. This is what the expression looks like. But first let's go to the Monitor tab for a second to see what inputs the SpaceMouse is actually sending. Okay, I am now manipulating the SpaceMouse, and as expected we can see that there are 6 axes for every degree of freedom the device offers. Sometimes it's hard to only move one axis without affecting the others, but we can pretty much see what is what. The numbers are positive when I move it one way, and negative when I move it the other way. Okay, back to the expression. I formatted it so it's a bit easier to read. Not that it helps much unless you're already familiar with the syntax, which I'm conveniently not going to explain in detail now. But basically the expressions use what's called the reverse Polish notation, which if you're old enough to remember Blockout, you might know from old HP calculators. For now I'm just going to say what each part does. You'll probably want to read the documentation on the project's GitHub repository before you go on to create your own expressions. Okay, whenever there's a number followed by store, it means put the value that's currently on top of the stack in the register with this number. The value on top of the stack is typically the last value evaluated by whatever happened before. So here we are putting the value 48 in register 32. This will just be a constant that we'll reference in the rest of the expression. Putting it in a register makes it easier for us to change because we only have to change it in one place. Okay, the rest of the expression follows a certain pattern. Each of these lines first fetches the input state of one of the axes of the SpaceMouse. These hex numbers are the same numbers we saw in the Monitor tab. This fetches the value from register 32, and this compares the two values. As you can see, we're using the value from register 32 as a threshold. It basically controls the sensitivity of the setup. If I saw a lot of accidental key inputs, I might experiment with increasing the number. Okay. Then we put the result of that comparison into register 1. So what this line does, depending on the input state of this axis, it puts either a 1 or a 0 into register 1. If the input is greater than the threshold value, it puts a 1, and if it's less or equal, it puts a 0. And as you remember, in our mappings we used register 1 for the right arrow key. Okay, the next line is similar. It starts with the same axis, so it must be for the left arrow key. The only difference is this. This multiplies the input value by -1 before comparing it to the threshold value. So if the input value is less than -32, it will put 1 in register 2. If the value is equal or greater than -32, it will put a 0. And register 2 is indeed used for the left arrow key. The rest of the expression does the same thing for the rest of the axes. This sets register 3, this sets register 4, and so on. Okay, I hope this will maybe inspire you to experiment with HID Remapper expressions. There's a lot more information about them and HID Remapper in general on the project's GitHub repository. If you have any questions, please leave a comment. Thanks for watching.